Hello everybody, this is a brief little thing talking about the graphs of quadratic equations. Now in order to know what a quadratic equation is, or what the graph is, we need to realize that the form of a quadratic is y equals ax squared plus bx plus c. The key part is that, of course, a cannot equal 0 because that would get rid of the x squared term. You have to, the highest exponent is a square, and then you have a quadratic equation. Now, when we graphed linears, we did tables of values so that we could see where the shape or how the points formed and then what the shape is. Let's do the same idea with a quadratic. So let's see what it's going to look like by making a table of values. For example, if we have the equation y equals x squared, let's just make a little table. Now, I made lots of values in here to make sure that we were very thorough in understanding our shape. Now, we have to remember that when we stick -3 in for x, remember, making a table of values, you get to choose x, plug it in, find its partner y. So when we choose a -3 in for x, we're going to have y equals, now the x is being squared. If my x is negative, the negative is being squared with it. A negative times a negative is going to be positive, so -3 quantity squared is 9. So the point that goes with, or the y value that goes with the x value of -3 is 9. We do the same thing all the way through for all of our values. A -2 times a -2 is a +4. Continue on with replacing, we're just going back into the original equation and replacing x with a different value to see what's going to come out for our y. Continuing on, we go y equals 1 squared, and we'll notice that, wait, 1 squared is 1. We already came up with a 1. That's kind of interesting to have the same y values and two different x values. Continuing on, we say, well, 2 squared is the same thing as -2 squared, so we have a repeat there as well. And the same thing for the 3. 3 squared is going to give us 9. So what does this look like if we plot these different points, because these are all different coordinates or points that are true for our equation? So what happens when I plot those points on a grid? Well, let's see here. Our first point was at -3, 9. So we go over to -3 on the x, and then all the way up to 9. And we find our point. Do the same thing. -2 was with 4. -1 was 1. 0 was 0. And then we had this repeat on the other side. 1, 1. 2, 4. Open the door. And 3, 9. And so it goes down and then it goes back up again in that fashion, and there's actually a curve to it. So if you connect your dots, woo, woo, you get this kind of curved or cup-shaped, U-shaped graph. Okay, we call this a parabola. All parabolas are symmetrical, meaning that the left side matches up with the right side. There's a line that cuts down through there, imaginary line that goes through this lowest point, and this is called the line of symmetry. It's not officially part of your graph. Your graph is only the red, U-shaped portion, but it's good to know that there is this line of symmetry, that the two sides are symmetrical or identical, and that you have a fold line, and that's what the line of symmetry is. The fold line always goes through this low point here, where you change directions from going down to going up. That point is called the vertex. Those are the important aspects of a quadratic. So once again, to summarize that in words, we have that the graph will always be cup or U-shaped with either a high or a low point, because the graph could open down as well and be a frown. We'll talk about that a little bit more in a moment. That high or that low point is called the vertex, as I just stated. And then there's that vertical line that goes through that called the line of symmetry. That's not an actual line. We just kind of use that as a measurement to make sure that our two sides are symmetrical. Okay. We know if the graph opens up because the a value is greater than 0 or positive. Now, what was a again? A is the number in front of x squared. Because once again, we're in the form of y equals ax squared plus bx plus c. Officially, it's called the quadratic coefficient. If a is less than 0 or a negative number, if we have negative x squared in the front or negative 2x squared, something of that sort, then our graph opens down and we're a frown. So nobody likes to make tables of values because they're long and they're tedious. So my next question is there a faster way to graphing quadratics? And lo and behold, there is! But the first thing we need to do is find the vertex. Now, finding the vertex is not terribly difficult if you remember this key component. The x-coordinate of the vertex can be found by taking the opposite of b over twice your a value. Once again, what are the a and the b? Well, we're always in this form. So a is the number in front of x squared, and b is the number in front of x. The c stands alone, the c stands alone, hi ho dereo, the c stands alone. The c is the constant at the end, without a variable. Once we find the x-coordinate of the vertex, you simply plug it in for all of your x's in the equation, solve that left side by using your order of operations to find what y is equal to. After you find the vertex, we identify if the graph opens up or down. Once again, that depends on your a value. Is a positive or negative? If you're in a good mood, you're going to smile and it's going to open up. If you're in a bad mood, you're negative and you're going to frown and it'll open down. Okay. Once you know which way your graph opens up, we apply the odd rule, or what I've deemed as the odd rule. We know in linear equations that there is a constant slope. Remember, slope is how you travel from one point to another point on your graph. It's a vertical and then a horizontal movement. And it was always constant in a linear equation. That's what made the straight line. You always rise 3 and run 1, rise 3, run 1, rise 3, run 1. Something of that sort, if the slope was 3, that is. Now, what happens with a quadratic is you have a sneaky little thing, the same idea, but it's dealing with odd numbers. Now, you're going to take the a value, which is the number in front of your x squared, and you're going to take it times the odd numbers, consecutive odd numbers starting with 1, 3, 5, 7, etc. That's going to give you your slope from the vertex to the first point on either side, and then from that point to the next point. So the slope is not going to be the same as when you square a number, they get larger and larger much faster. Refer to our exponential growth and decay discussion. Wow, that's a little bit confusing, isn't it? Let's see an example of that. Say I have the equation y equals x squared plus 2x minus 3. The first thing we need to do is find the vertex. We find the x-coordinate of the vertex by the opposite of b over 2a. Now, whenever I'm dealing with a quadratic, I always take time to stop and say, wait a second, what are my a, b, and c values? Because oftentimes I need to know what each of those are. So a is always the number in front of x squared. Once again, if there's nothing there, there's always a 1. Because 1 times anything is anything. 1 is the god of mathland. He, she, it is always with us, whether we see him, her, it, or not. Because 1 times anything is anything. B is the number in front of x, which is a 2, and the c, as I said before, is at the end. Now remember, the sign in front of the term goes with the term. So the c in this case is a -3. Now to find the x-coordinate of our vertex, we substitute in. We have the opposite of b over twice our a value. The opposite of b simply means that if b is positive, it becomes negative. If it's negative, it becomes positive. B is a positive 2, so I'm now going to make it a -2, all over 2 times my a value, which is 1. Simplifying that, we have -2 over 2, or the x-coordinate of my vertex is going to equal a -1. Now we have to find the y-coordinate that goes with that. Once again, go back into your original equation, replace all of your x's with the -1. So we have y is equal to, now it's the x that's being squared, so you must have parentheses around that -1 because the negative is being squared also. 2 times -1, oh, I'm running out of space, -3. So we're going to have y is equal to -1 times -1 is 1. 2 times -1 is a -2 and -3. Do your order of operations left to right to make sure that you don't screw up your signs. 1 minus 2 is a -1. -1 taking away 3 more makes a -4. So my vertex is the coordinates, because it's a point, it has to be in coordinate form with parentheses, -1, -4. Next, I apply my odd rule. And I say, okay, A once again was 1. So I'm going to take 1 times all my odd numbers. Okay. Well, 1 times all of my odds are just going to give me my odds back. So my slope is going to be 1, and then 3, and then 5, and then 7. Now remember, slopes are a rise over a run. So you need to write these as fractions. Whole numbers as fractions are over 1. Okay. Now let's go through and plot our points. The vertex is at -1, -4. So I go down here, my graph, -1, -4. There's my vertex. Now remember the rule of symmetry. My A is positive, so my graph is going to open up. So everything's going to go upwards. Now my first slope was 1, so from this point I'm going to go up 1 and over 1. But I also have symmetry. So if I go up 1 and back 1, I get the symmetrical point. Now from that new point, it's got to be from that new point, I'm going to do my next slope, which was a 3. So from this point, I'm going to go up 1, 2, 3, and over 1. Same thing from this other point. I'm going to go up 1, 2, 3, and back 1. Yes, it definitely helps to make the cute little sounds as you're graphing. Now I'm going to continue on. My next slope is the 5, so from this new point, I'm going to go up 1, 2, 3, 4, 5, and over 1. Same thing on this other side. Go up 1, 2, 3, 4, 5, and over 1. I think that's enough because if I go up 7, my next one, I'm going to go off the top of my chart. As you can tell, they rise relatively quickly because of the squares. Now I can see all my points and the symmetry. Remember, these are just counting dots that I had in between here. It's not part of my actual graph. Now I get to connect the dots. Remember that there's a swooping to it, so you might want to make sure that you have a little bit of a curve going on, and that it's not rising straight up from this point. It's all constantly going outwards. Because of that slope of 1, we're always moving one more step outwards. And there you have a fairly decent graph of a quadratic, a nice little parabola. You can tell the line of symmetry here, going through x equals -1. That's that x-coordinate of the vertex. And the two sides line up. And just like that, you've graphed your quadratic without having to make a table of values. Once again, if a was negative, we would have done that same idea, but we would have gone down instead of up and over. We would have gone down and over instead. So a little bit of a summary on what we know. So a summary of what do we know about the graphs of quadratics. So if we were given an equation, how can we quickly tell what this equation is going to look like? Well, with it being a quadratic, we know the shape. The shape is called a parabola. It's a U-shaped graph, or a cup. Okay? It always opens either up or down, never on its side. We know whether it opens up or down. Up if a is greater than 0, down if a is less than 0. We know that it has a vertex, which is the high or low point, where it curves. And we can find the x value of the vertex by taking the opposite of b over twice our a value. Once we know that, plug into that value into the equation, for x and solve for y. And if you think about the 1, 3, 5 rule, if your a happens to be a number that's like 2, 3, 4, 5, when we take it times the odds, it means that our slopes are going to get pretty steep, and so our graph is going to be kind of skinny. If the a happens to be a fraction between 0 and 1, say 1/2 or 2/3 or 3/4, something of that sort, when we take that times the odd numbers, it's going to spread our graph out, so it's going to be a bit wider. So just by looking at the equation and identifying your a, b, and c, we can tell what exactly our graph is going to look like.